Hello, everyone. My name is Darwin. I work for GitLab. I want to talk to you a little bit about the architectural trade-offs for GitLab Runner workload authentication and authorization into cloud environments. So we get the question, how can we set this up so that a GitLab Runner can access one of our 10 or 100 or 1,000 accounts in a given cloud provider? And this is a growing consideration for large organizations or any organizations that are using cloud accounts as a fundamental security boundary for development teams. So let's dive right in here. First, I'm going to reflect the three ways that we do this. The first way we have is cloud keys and masked variables in GitLab. This is a pretty common first level permissioning that you see in most products. This is not the most secure way to manage cloud authentication, both in terms of where you're storing this information, as well as the fact that you're handing out keys that you may or may not be actively rotating. There are benefits and challenges. So as we go through all three of these, you'll see that there are architectural benefits, even for something as straightforward as keys. And then the IAM rules assigned to compute. When we assign IAM rules to compute, and then we put that runner compute inside of the cloud account that we want to access, we get this nice capability that anything sent to the runner has whatever permissions you assign to it. This is a little bit better than keys since there is no authentication involved. But the other challenge that you have is that authentication is one for all for every job that runs on that runner. Then finally, we have OpenID Federation, which is your OIDC JWT token capability that allows you to get very granular about your mapping between GitLab and a given role in a cloud account. When you use this, you can get as granular as a given branch inside of a given project is mapped to a certain role. You can also use wildcards when you set this up so that potentially just a given group hierarchy is all mapped to one account. So you have a lot of flexibility here. So it's the most sophisticated. It's also does not have the problem of sharing secrets because you have actual federation between the systems. It does require that you federate each Amazon account into your GitLab instance so that this can all work. I want to show you now a tradeoff visualization that allows us to look at this information in a slightly different way. This is a spectrum here, and when we go through this information is purposely reflected as analog, not quantitative. We are really kind of giving a rough measure of where this might be. You might even evaluate this and say, hey, you're not putting these in the right analog spot. At our company, we'd put them over here, and that would be perfectly fine. I think this is actually a powerful way to do it because a lot of these decisions can't be boiled down to quantitative concerns. And even if we start giving things a rating of a 1 or a 2 or a 3, really we're doing pseudo quantification. So we start creating numbers that roughly represent something that's rough. In this methodology, we just leave it rough. So I'm going to put keys here at this point on this spectrum of runner management effort. How much work does it take to manage the actual runner instances themselves? Put assigned to compute over here to requiring more runner manager effort, and then OIDC and JWT over on the minimum side. What this basically means is the more that we are to the right, the more likely we can use a highly shared runner, for example, an auto-scaling cluster of runners to access a lot of different Amazon accounts. Now, these considerations of this green box is backed by a variety of sub-criteria, so to speak, or sub-trade-offs. And so one of those is pipeline mapping flexibility for permissions. So with OIDC, you have the maximum. And then when you go over to assigning to compute, you have the least flexibility in terms of mapping various projects, branches, and Git refs in GitLab into a specific permission set. Also, the location of the runner, if you're assigning it to cloud compute to give it cloud permissions, then it has to be in the cloud. Where on the other side, we don't really care where the runner is because it's not using its location, so to speak, as a way of establishing permissions. And then finally, runner sprawl. So when you assign to compute, you are then causing compute to be a fragmentation boundary for security concerns. In other words, if I need 20 security contexts, then I'm going to need 20 runners. Pursuing that approach causes more fragmentation. Next is recurrent daily human processed complexity. What does that mean? That's the stuff we can't automate. And sometimes when we automate, we actually go backwards on this because our team gets more automated, but another team in the organization actually has more recurrent daily human process complexity, or we basically didn't really automate something if we end up balancing these two things to zero. If we end up causing more human toil, we've actually unautomated in a way, because the whole idea of automation is to swap machine toil for human toil. So with keys, I'm going to put it here, assigned to compute over on minimum and maximum for OIDC JWT. This is because the administration complexity increases. So administering this day to day, setting up roles for new accounts, all of those things has to happen by humans at some point. Then developer user complexity. So how complicated is it for your developer users? OIDC JWT tends to be more complex. Here's a key to reading this diagram. Notice in the bottom right that the flagpole with a broad bottom indicates that you have a range of outcomes along this spectrum based on how you implement. So in the case of OIDC JWT, if you decide that you're going to be very granular in what roles you assign to what contexts on the GitLab side, you can make this even more complicated. So the more specific you get about how you design it, the more complicated it becomes. And you can also back that off and say, hey, we want one role for this entire group hierarchy, and make it less complicated. So that's what that means, that you have your choices within how you design this could drive that harder. Then architecture and engineering complexity. So when you first set this up, thinking through exactly these trade-off matrices we're talking about and putting together something that works for your company that has a reasonable admin overhead. Well, so keys are over here. It's pretty straightforward. Compute somewhere in the middle, and OIDC JWT moves to the left. So you're going to have to spend more time figuring out how to make this work. And then we have another second set here. If you are focused on doing self-service, so developers have to figure out themselves how to map OIDC and JWT into the target environments, if they're responsible for finding that information somewhere in your organization and coding up their own OIDC mapping, then of course you're increasing their design complexity. They hopefully only have to do that once at the beginning, but it can be more challenging. Then we have security best practice, so lower on the left, higher on the right. We have keys over here, assigned to compute sort of in the middle, and OIDC JWT on the right. One of the aspects of this is credential exposure risk. So you have more with keys, very little with assigned to compute. And because OIDC is using temporary tokens, you have no risk there. And then automatic credential rotation. This is, in a way, it's NA on OIDC, and there's more effort to make that happen with keys. And then are permissions automatically granted to CI code on keys? Yes. And then on OIDC, you have to opt into OIDC to turn it on for a job. So there's a little bit of control about whether every job ends up inheriting those permissions or not. We have the key again. One thing I want to mention is you want to be careful of two things that are what I call ideological architecture. One is that you only need to pick one of these models. By only picking one, that's sort of the architect's best world, is to have one model to suit all, but frequently this is pursued to a bad end run. So you might have a situation in your organization where 80% could use assigned to compute just fine, and the others should use OIDC or something similar to that. But if you force it to be the most sophisticated approach for everything, you can end up violating Pareto's law, and you end up spending a lot of time on creating, say, OIDC settings for repositories that aren't benefiting from it. An example of this would be sometimes deployment compute is better assigned to compute because you can shut down that runner when you're not using it, give it only deployment permissions, and have it in the target environments. And so don't be afraid to pick more than one model, making sure that you take a look at what are our use cases. And so if we have use cases that can be forced into two models at a great savings instead of picking one model and having, a very high cost, then that might be a good idea to think about that. So don't pursue one size fits all type architecture. The other challenge we run into is, if I pick the most sophisticated, I'll be safe. I'll never run into any limitations. And so that's a way of deferring a decision. That's also a decent architectural disposition in general. However, I'm trying to show with these diagrams that picking the most sophisticated also introduces complexity. And some of that complexity is human complexity that you can't automate. This is the basic lay of the land in terms of the trade-offs for architecture. There's one other thing I want to highlight. We're going to go in the next slide into controls you have in GitLab for code merges, because no matter what you do here, now that you set runners up to be able to have permissions in environments, now within GitLab, you have to be careful to make sure that you understand that if someone can merge code into a repo bound for one of these runners or using some of these runner permissions, they now essentially can obtain those permissions, even though they personally have not been granted them. So it can be an attack vector. There's a lot of controls in GitLab that you can then take control of how merges happen, who can merge, who can deploy, and there's all kinds of controls. And next, we're just going to take a quick look at an overall slide that shows you the full raft of controls. There's another video that actually goes through each of these controls that I'll forward reference for you. Here is the overall picture of the controls that you have in GitLab to start controlling what kind of jobs can run on runners. Every job in a pipeline can run on a different runner, and those runners might have different permissions according to what we just looked at previously. These purple boxes are the ways in which you can control what code merges to what branches and therefore uses what runners. There is a full video that explains each box with a certain amount of detail, and that link is right there on the screen. But I wanted to let you know that you have these two layers. So once you establish kind of runner permissions on the compute level, then you can also start working with some of these controls to make sure that the right folks can do the right things with the right runner permissions into your cloud environments. So this has been architectural trade-offs for GitLab Runner workload authentication and authorization into cloud environments. I'd love to hear from you if this has been helpful for you, and I'd like to hear feedback too on the visualization format if that's something that works for you for architectural trade-offs. Thanks so much.